Cek, cek. Nyala nggak ini? Nyala. Cek, cek. Cek, cek. Okay. Okay, let's start this seminar today. Good morning, everyone. So this week is our turn for this Wednesday seminar. So now it's the turn for the geoscience specialty group. And we have a special guest today. Well, we have a special guest for the seminar today, but our guest is actually stay in our geophysics laboratory since, I don't know, 2 or 3 months ago. And will stay in our lab for the next few months. And okay, let me introduce our guest for you who don't know him yet. So we have uh, Romain Brossier. He is a associate professor in Université Grenoble Alpes. This is a university in France, in the city of Grenoble. How do you pronounce Grenoble? Grenoble. It is a beautiful city. So you have a maybe small city with the view. You have a European Alps mountain in the background. So it is very beautiful city. And you will present about recent advances in high resolution seismic tomography. This is quite a geophysics heavy thing, but there will be also some mathematics involved. So if any of you came from Department of Mathematics, it will be interesting for you to know the application of mathematics in geoscience. So yeah, let's start the seminar today. Let's give the room for Pak Roman. And also I'm hoping that our graduate student will prepare some questions for him later. Okay, let's start. Thank you. So
okay, you hear me? Yes. Okay. So hello everyone. So thank you very much for inviting me for this seminar. Thank you for the introduction, Pateo. So today I will present you some recent work that we perform in our research group at Grenoble University in France. So as I will show you, most of our research is dedicated to what we call high-resolution tomography from seismic data. And I will, after a brief introduction, I will show you two recent development that we performed for the past few years related to what we call noise-based data. So I will show you what it's about, and also uncertainty quantification. So the starting point of this presentation is the fact that when we have some subsurface targets and we propagate waves inside, we have some quite complex wave phenomenon which appears. Here is a simulation in a realistic 3D models from a trust offshore Japan. So it's a subduction zone, and a 3D model has been designed by one of our previous postdocs. And we are simulating some seismic waves inside. And what we can see is that we have a quite complex wave field with some, I would say, direct P wave, refracted P wave, but also many complex waves that arrive on the seafloor, conversion from P to S, short waves. And if we have a look to a profile that we could have from OBSs deployed on the seafloor, which is quite common to do. We made such kind of targets from active data. We have this type of data. So what is very oftenly used, our first break, to be able to do some first arrival time tomography. We can also have some reflected waves that can be picked and analyzed. What we are trying to do in our group is more to taking this whole wave field as input of a tomography, which means that we take the full waveform recorded by sensors and we perform a tomography. So we solve an inverse problem, taking as input those observed data from an unknown real Earth. And we are trying to solve an inverse problem from an initial model. We simulate the whole wave field in this initial model. So that means that we need to simulate the wave propagation in 3D models. So this is quite a computationally intensive task in order to have this calculated data to be able to compare with the observation. And then we feed an inverse problem where we define a misfit function that we want to minimize iteratively by updating our model in order to fit better and better the data. And hopefully, at the end of the iterative process, we have an updated model which is realistic with respect to the targets that we don't. Then we can do some geological interpretation, petrophysical interpretation on those kind of models. This model actually is a model of seismic velocities. In this example, this is the P wave velocities. And we will discuss later different parameters we are able to retrieve, but they are very often seismic velocities that affect the seismic wave. So this kind of methods is, I would say, for the past 10, 12 years now, a kind of standard in exploration, so in the industry, mostly oil and gas industry. And the reason behind is that it provides quite high resolution model of the subsurface. Here is an example of a 3D velocity model obtained from industrial data. Here, you still hear me? So this model is obtained by using only a reflected wave. And if we use the full seismic data, you can see the amount of details which are added in the 3D models and also on those horizontal sections at different depths. And thanks to those velocity model with high resolution, we can have an interpretation, geological interpretation of the subsurface from those velocity models. So basically without migration steps, which is a qualitative image. Here we have quantitative image of the velocity. Here it's applied under the acoustic approximation. So we assume the Earth to be an acoustic medium with only P waves. And this acoustic-based FWI is now a standard in the industry. So if I show you the main workflow of full waveform inversion and the associated difficulties of each step, you can see that we have basically many problems to solve. So we need to start from an initial model, and of course, we need to design an accurate enough initial model. It's not an easy concept to figure out what is a good enough mean. We need to start from some observed data, which have some dependency based on the quality, density of acquisition, the frequency content, so depend on the instrument, depend on sources. And this observed data has to feed a misfit function. Many questions arise here on the definition of this misfit function. The usual way is to take just a point-to-point comparison of the seismogram, or evolved things can be also designed. From the model, we need to solve the wave equation. So mean solving the 3D wave equation in acoustic or elastic medium, which is a quite mathematic and computationally intensive task with a computing cost which increase in frequency power 4. So you see that if we double the frequency, we multiply by 16 the computing cost, so which is a quite difficult problem to solve. From this forward modeling engine output, we can have the synthetic data to feed the misfit function. Having the synthetic data and observed data, we have this misfit function, and then we have all the inversion part. This inversion part involves a number of steps. Usually we use local-based optimization, so we need to have the gradient, the first derivative of this misfit function, to be computed, which involve again some modeling. And then we can update our model of parameter and loop over this workflow, generally several tens of times. So each, I would say, orange-based point here is basically either a geophysical, mathematical, HPC, so a computing issue that we need to solve. And for today, we will focus on two of those, I would say, problems and propose some solutions for them. One is about data, because usually we need in such kind of approach to have good quality and dense data, but at large scale, it's not always easy to have earthquake everywhere, to have uniformly distributed sources. So I will show you how we can manage things from noise, actually. And the update here of the model leads at the end to a single model of the subsurface, and it's good to assess the uncertainty, the quality of this output model at the end of the workflow. So this is the roadmap for today, discussing how to enrich the data noise-based measurement and how to assess. So, you still hear me? You hear me? Oh, sorry. Yes, you hear me? Yes, it's okay? Good. So, so based on that, we will now start with the first topic, which is to deal with elastic waveform inversion. So not only acoustic, but we want to retrieve both S-wave velocity and P-wave velocity. And we will use as input data something coming from ambient noise. So what's the theory behind that? In fact, as I discussed before, acoustic FWI is quite standard now, but most of our waves in the subsurface actually come from an elastic propagation. So if we go toward elastic, we are able to better handle complex wave phenomena, as a conversion from P to S wave, as surface waves. And as we have a better physics, we are also able to reconstruct more parameters the waves are sensitive to. So we should have a better view of the subsurface. The difficulties related to elastic FWI are, on the one hand, the computing cost, roughly speaking, between 10 to 100 times more computationally intensive than the acoustic version because of the more complete physics. And also, on the inverse problem part, as we have several parameters, if you already did some inverse problem, when you have several parameters, it's not always easy to separate the contribution from the different parameters. So we have some crosstalks, some links between the parameters that are not easy to manage. And when we consider more complex physics, we include more complex waves, it increases also the nonlinearity of the inverse problem. So in the frame of this objective, one question is how to design sufficiently accurate starting model for both P and S wave. So the one idea to design such kind of good quality data is to take benefit of ambient noise recording. So we can show that if we have some diffusive regime of wave propagation, if we take cross correlation of time series, we can converge under some condition to the green functions between the two stations. So if we record noise at two stations sufficiently long and we have a uniform distribution of sources, at the end with those two very long time series, the correlation of both give the green function between the two receivers. So this statement has some background in statistical physics and acoustic, and it has been shown in the early 2000s by Michel Campillo and Anne Paul, who are actually a professor in my laboratory in France, that for the Earth it actually works. So we can use very long seismic time series and use cross correlation to retrieve what we can call empirical green functions. And since then, many applications have been done at regional and local scales. So here is one early application of those techniques by Laurent Stelly during his PhD work at that time. So you can see here is Europe. You have here a network of stations. And in his work, he used the cross correlation of ambient noise between all the pairs of stations, use those correlations to retrieve some green function. You can see them here between the different components, so vertical correlation, radial, vertical, and vertical radial. And from those green functions, either phase velocity, either group velocity dispersion curve can be picked, and a local 1D velocity model can be obtained. And by doing that for each of the pairs of stations, an approximated model can be obtained under the European continent here. In fact, this property of retrieving green function has been, in fact, conjectured much earlier for exploration by Claerbout at that time, in the 60s, where he discovered that the autocorrelation of ambient noise from surface measurement gives the zero offset reflection seismograph. So the use of this technique, in fact, has some background that almost 60 years ago by John Claerbout in the exploration frame, and then has been applied at many scales. So you can see here an example of active reflection data, and the same that we can retrieve through cross-correlogram. So there are, of course, some background artifacts here, but you can see the reflection that we can retrieve here. So in the seismological scale, we usually retrieve Rayleigh waves. Here you have an example with body waves at exploration. And what I will show you after is mostly driven by surface waves because we are working in a more seismological. So this kind of application has been also applied to crystal scale data. So here from an exploration scale from OBC data by Aurélien Mordret about 10 years ago. And you can see here the negative and positive part of the correlation, which are actually green function from one station to the other. And the reverse side is the reverse path of the green function in two frequencies. This kind of here it's short wave can be used again to derive 2D group velocity map under the subsurface, and then in the local 1D shear wave velocity model, as can be applied before by Laurent Stelly, but here at a crystal scale, as you can see, at very shallow depth, few meter depth below the. So the question from this background is, can we do better? Can we improve the methods and go beyond the local 1D approximation that we do to fit dispersion curve? And to answer this question, the point is, can we use 3D elastic-based FWI to have higher resolution 3D models? So this is actually what we can do. If we go back to the green function definition that we retrieve from the cross-correlation, in fact, we can use this empirical green function and convolve it with a filter or a wavelet. And this convolution of green function by a wavelet can, in fact, be directly our observation that we use in full waveform inversion. So we can directly take the green function, convolve with a wavelet as observed data. If we then use the same wavelet to feed our forward solver, we can compute the calculated data. So we have everything in hand, the observed data coming from the green function, the calculated data coming from our forward simulator. And then we can just do, let's say, inversion. The only limit behind that is that the green function we retrieve here with a cross correlation is trustable on the phase point of view, but not on the amplitude point of view. We can show that the amplitude is basically wrong. So we need, therefore, to modify our misfit function to not consider amplitude, because we know it's wrong. So we need to define a misfit function which is kinematic only, as the one proposed by Carl Tate about 15 years ago, based on some multi-taper phase measurement to capture only the kinematic of the misfit and discarding amplitude. So I will show you two small applications. Okay, it's okay. So after this this first stage, we have used the empirical green function from those, I would say, pairs of stations. So you can see that we cannot use all of them. And depending on the frequency, not all of them are usable. To design 2D group velocity maps that have been then inverted to 1D velocity model with Geopsy. And that gives a pseudo 3D initial models for the target. And thanks to this pseudo 3D S-wave model, P-wave model from first break picking and tomography, we have been able to run this elastic FWI-based approach. So you can see here one section below the landslide, and one important finding has been this higher velocity zone that we have here in the middle of the landslide that were not actually well understood and characterized before. And in fact, this higher velocity zone, in fact, match very well the dynamic of the landslide, which is observed on the surface. Basically, on this landslide, there is on the top part some plastic slide of material, which then accumulate in the middle. And after some accumulation, there are some triggering of movement, which are more fluid-based motion that goes towards the lake. And in fact, this accumulation zone was not well understood because there is no real topography evidence of changes. But in fact, this is directly related to the anomaly we have in the bedrock that we have on this high velocity zone. So basically, this high velocity seems to be the part which generates this accumulation and therefore explain the whole dynamic of the landslide which is observed on this target. So here is just a few examples of data fit. So in black, the observed data, in blue, the initial, and red, the final. So you can see how this waveform-based inversion has been able to improve the fit for the different frequency band. And therefore, give again at this scale, even if it's relatively challenging because the noise distribution is not easy, allows to give good 3D models that can be interpreted here from a landslide point of view. I will now go towards the second topic of this seminar with uncertainty quantification. So you may know that for a linear inverse problem, it's relatively easy to get access to uncertainties through the covariance matrix, even if sometimes these kind of objects are big to manipulate and not easy to manage. But at least from a theoretical point of view, we have some tools. For the full waveform inversion, the problem is we are dealing with a non-linear inverse problem, a large size inverse problem, and therefore uncertainty quantification is a big difficulty, and therefore we need to see what is possible for such kind of problem. So as we discussed already, we have a non-linear inverse problem which is ill-posed. And we also have some dependency on the design of the initial model. The design of the workflow we follow to obtain our models. And we have also some hyperparameters about smoothing, tuning, and so on. So we are sensitive to all of that, and it's therefore not easy to estimate the uncertainty with respect to all of those parameters. So what we can see in some textbook and usual literature is that if we want to assess the global uncertainty of an inverse problem, we need to rely on Bayes' inference theorem, which basically we can tackle with some Bayesian formalism, with a Markov chain Monte Carlo or Hamiltonian Monte Carlo, but basically we need to have a very large number of sampling of the probability function to be able to estimate this probability. We also have some more recent proposal to sample this posterior function, but all of them, again, rely on a very large number of samples. And for computationally intensive problem as a full waveform inversion, it becomes very soon impossible to use such kind of technique to assess uncertainty. So therefore, we need to move toward what we could call local uncertainty quantification, which means that we do not want to sample the whole function, but more to assess how we can trust the results from a local point of view. So this can be done basically by approximating what we call the Hessian, so the second derivative of the mystification, with a, I would say, smart approach to limit the computational cost. So the idea, therefore, will be to probe this inverse Hessian, but still managing the computing cost of the probing. So what we propose to do for this probing is to rely on what we call ensemble Kalman filter. So those kind of techniques are widely used in weather forecast or climate forecast. So the approach usually applied to dynamic system, and they rely on an ensemble of particles that I will explain just after. So basically, they are able to be applied in parallel because a different ensemble can run in parallel. And the idea was then to adapt those kind of approach to the full waveform inversion context. So I will present you after that an application to a 3D data. So what's the math behind? Basically, instead of relying on a single model of parameter, we rely on an ensemble of model parameters. So each M subscript I is a model, and we have an ensemble of models. From this ensemble of models, we can compute usual statistics, the mean, and the covariance matrix that we can compute from the variance of those models. So therefore, this covariance matrix P, if the number of models is relatively small, is what we call a low-rank approximation of the true covariance. So we have a limited number of information about the full covariance. The idea is therefore, instead of running a single inversion, to run an ensemble of inversions, each of them with a different model. And the idea will be to analyze where the different models goes towards the minimum. And thanks to this ensemble of models, we will be able to tell something about the uncertainty. So the whole workflow can be summarized as this scheme. Basically, we have different steps. In weather forecast, that would be some days, basically. Here for us, there are steps associated to a subpart of the data. For each subpart of the data, instead of running a single inversion, we have an ensemble of models. for each of them, we are doing basically a full waveform inversion for few iterations. So we are iterating on those models. From this ensemble of models, we end up with an ensemble of reconstructed models. And from that, we can derive means and covariance. After this step, we can compare to another part of the data, the one from another step. And here is what we call the analysis part of Kalman filter, which is a kind of linear inverse problem to, I would say, improve the ensemble of models with respect to the fit to the new part of the data. So they shift basically the family of ensemble, new sets of parameters. We have new observation. So we can run again FWI, so inversion. Have an ensemble of solution. If we have another step, so with another part of the data, we can do again this analysis, and so on and so forth. So therefore, we rely on an ensemble of particles. Each particle is a subsurface model. And we run the inversion for each of those particles. And from step to step, we are doing this analysis step with a new part of data that were not used before in the previous step. So it's a kind of predictor-corrector scheme that we can have in numerical analysis. So I will be fast on this slide, which is quite mathematic, but the key point to remember from that is that basically the computing step is a forecast. The analysis, basically, we are manipulating small size object and doing a small SVD on a matrix which has a size of number of particles in the model. So basically few tens. So there is no big challenge in terms of numerical analysis on this step. So basically, at the end, we are able to run in parallel a number of members in the ensemble. And for the analysis, we rely on few algebraic manipulation. And thanks to this ensemble view of the problem, we have access to a low rank approximation of the covariance. The question is how to design the hierarchical workflow, how to cut the problem in different steps. So it can rely on frequency continuation. In fact, this was what we proposed originally with this approach with Julien Turin in the end of year 2010. It can be through time offsets, windowing, and it can be by selecting the shots in the whole data sets, because usually we not able to manage all the shots at once. So we can therefore cut the problem thanks to a random selection of. And this is actually what we have applied to this application that I will show you right now. So in fact, we are using here an industry-based data sets. So we have about 50,000 shots. So all of them are red points here. And some cables of receivers on the seafloor. So it's a shallow water environment data sets. And we are running acoustic-based full waveform inversion. And in this example, for most of result, I will show you using 50 members in the ensemble. I will show you some comparison at the end, depending the size of the ensemble. And basically, thanks to reciprocity, we are using the 2048 receiver as shots, and we randomly select those shots in the steps of the ensemble transform Kalman. So what does that give after? We need to start from an initial model. So here is the mean initial model of the ensemble. And you can see here the prior variance of the ensemble design. So you can see that at the beginning, we start from something which is homogeneous in terms of variance. The design of all the model is already a quite challenging part that we can discuss during the question session if you want. After running the ensemble approach with 50 members, here is what we have in terms of mean model. So if we take the mean of all of the 50 members, we obtain these results, in which we retrieve the main geological feature we know from this target, which is basically a gas cloud around 1.5 kilometer depth. We have some gas layering in the sediment. We have some shallow gas also here. We have some channels very shallow below the subsurface. So the mean model resembles very much what we could retrieve from usual acoustic inversion. Then what about the variance of the ensemble? So the variance is the diagonal of the low rank covariance we have from the ensemble. So you can see here the variance map associated to the mean velocity map. And there are some red dots just to be able to make a point-to-point comparison between the velocity and the variance. What we can see here is that basically you have some high variance values, which are here, and that are directly related to the localization of layers. So in fact, as soon as you have a layer with some uncertainty on the velocity, that leads then to a possible depth shift of the event, which leads to a higher variance in terms of uncertainty. In the homogeneous constant, velocity region, the variance remains relatively small because there is no ambiguity here. So as soon as you have some layering and thin layering, you have higher variance in the output. So this is already an interesting output from this analysis, localized higher uncertainty region. If we have a look to the prior and posterior covariance, you can see here for this each time the position of the red dots, how the initial distribution in the ensemble look like compared to the final one. So you can see that we started from something very homogeneous, and after inversion, we have possible shift in the velocity and spread about the uncertainty depending the position of the point we are looking at. You can see that for this shallow point inside the gas, we have a shift and a small spread after inversion, while on the layer here, we have a much larger spreading due again to the uncertainty associated to the position on the. So again, which gives confidence in the information outputted from this low rank variance information. We can also have a look to correlation matrix. So here we extract information from the off-diagonal term of the low rank covariance. And in this case, we are looking at small boxes to see the correlation between parameters, so the spatial correlation between parameters. You can see that if we focus on this point, we have strong correlation horizontally inside the layer because we have the same velocity basically, and then negative correlation as soon as we are on the higher velocity zone here. So that gives an information about the local resolution and how the parameters are locally correlated one with each other. thanks to this local correlation view of the parameter. We may question about the reliability of those estimations depending on the number of members in the ensemble. What we did is to run the same setting, but for 3 sizes of ensemble. So one ensemble of size 10, one of 50, these are the results that I showed you before, and one with 200, so 4 times more. What we can see that for this problem, which involve several millions of unknown in the tomography, we have results between 50 and 200, which are very similar. So the spreading, the Gaussian shape that we retrieve after inversion is relatively trustable in those both cases, which means that basically at 50, we converge toward a reliable information thanks to the ensemble. For 10, this is clearly not the case. With 10 members, we are not able to capture at all a Gaussian shape in terms of variance, both in the prior and in the posterior. So this is an important kind of information because we see that for those kind of industry scale data with already 50 members, it's enough to capture the main trend of the posterior covariance in the out. Just as a remark, those kind of ensemble Kalman filters, they are basically routinely used, for example, by weather forecasts, as German weather forecasts. They use such kind of technique, and they usually apply it with 40 to 50 members in the ensemble for weather forecast at the European scale. Again, with millions of unknown in the weather forecast. So you can see here, again, this convergence based on the number of ensemble members, now on the correlation matrix, with again the same conclusion. We have a convergence from 50 with a good consistency with the result of 200, while the result at 10 is clearly lacking some convergence, and we have not reliable results with this too small size of ensemble. So we are reaching the conclusion, so, which will be relatively short. So I try to show you that we can use the waveform information to derive high resolution models of the subsurface. Of course, you need to take benefit from dense array to have enough data to constrain this large scale inverse problem. But on the other hand, we can apply it at basically all scales with the same kind of technique, each scale having its own difficulties, of course. And more specifically, I show you how we can use the continuous recording of a noise to derive empirical green function that can then be used as input for this kind of tomography at 2 different scales. And the challenge behind uncertainty quantification with one proposition that we did with the ensemble-based Kalman filter. So we are currently working on alternatives of this ensemble Kalman filter to maybe have a better sampling or different sampling of the posterior distribution function. Maybe not to decrease the cost, we'll see, because this is clearly one challenging problem, the computing cost uncertainty estimation. So done on my side. Thank you very much for your attention. Thank you for the invitation for me to stay here for several months in Georgia. And, thanks, usual thanks to our sponsors and computing facilities. Be able to hand up with this kind of things.
Okay, thank you for your presentations. It's an interesting one. And I apologize for our online audience for some audio problems we had. I hope that you can still enjoy the presentation. So next we have plenty of time for discussion and Q&A session. Is from our audience in this room, do you have any questions? Ada mikrofon lagi nggak?
Can you go? Can you go for the slides 40? Or slide 4 or 40? Yes.
Yes.
I wondering about this panel. In panel A, we clearly see the uh, white anomaly clearly visible in uh, panel panel E, but it disappear in uh, panel B and C. Does the full waveform inversion? Uh, I just wondering what happened behind the scene. Why the large anomaly disappear in panel B and C?
In fact, the different panels here are associated to section at different depth. So here is a shallow section. Here is the second one, and this one is the third one. We are seeing different depth in the same model.
Or it's because a different, not because the. Oh, okay. Thank you.
Okay, another questions maybe?
Okay, thank you. I will ask about from the cross correlation of two receiver, we get positive and negative time lags.
Yes.
With time that we use to process until we get dispersion curves.
Okay, so in the usual workflow for 1D inversion, what they usually do right? Okay. Yeah. So what is usually applied is to select the paths which are relatively symmetric in the positive and negative leg. Because this is a kind of a signature that the source of noise is well distributed. So if they are relatively symmetric, using one or the other doesn't really matter. And usually they use a mean of the two.
Another question. In the example of landslide project, you use 100 geophone, 33 days measurement with 5 hertz geophone. Yes. I have and that measurement get the depth until 100 meters, about 100 meters, if I not mistake.
Roughly speaking, yes.
Yes. I have implement in my experience, I have implement 24 geophone vertical in MASW, active and passive, with the recording time only 30 seconds. Which one is better to map the beneath of the earth? But yes, different quality, or
here's we have 30 days of data, so not 3 days but 30. And even if the geophone are 4.5 Hertz geophone, we are able to go down to 1 Hertz data. 1 Hertz. If you see the very first band, here is the data in the 1.5, 2.5 Hertz. So thanks to the ambient noise and the fact that we have sufficiently long time recording, we are able much lower than the peak frequency of the geophone. And that's why we are able then to go at a large depth. So with 30 seconds of record, I guess that is not enough to reach this low frequency noise.
So longer time is better.
Yes.
Okay, thank you.
Other questions from our audience in this room?
Okay, thank you very much for the talks. Actually, I got several new things because since I left, there are a lot of work that has been done. And I'm curious about the application of the ambient noise for to use the active data as well to constrain the VP a bit better, probably. And for the earthquake, for the regional one.
For the regional?
Yes.
Okay. It's a good question. In fact, at the Alpes scale region, what can retrieve from noise only surface relay and we can pick some earthquake-based data. The point, frequency content of this local seismicity is much higher frequency compared to the frequency here. So, which means that for now, we version connect the computer because we have modeling, not inversion, but modeling to create wave a local earthquake, which fit quite well, in fact, the observation, even for the P wave phase. The P wave model we derive from relay wave actually allows to predict quite well the higher frequency P wave from local earthquake. And the ambient noise-based tomography has been used as input and starting model for local tomography, but only to improve a little bit the velocity model, in particular at shallow. so where we don't have resolution with Rayleigh. So he has improved the model at shallow to improve again the fit of local earthquake. But it would be a next step to go toward waveform inversion of local earthquake. But it's challenging in terms of computing cost. Yes. We have 200 inversions in parallel. Yeah. 200 times more. Yeah, so that's why we prefer to stick with 50 rather than 200. But yes, we could. Yes, we could. Yes. No, we, in fact, building the initial sets of members is already a quite difficult step. Difficult. Difficult in terms of knowledge to inject, but also in terms of mathematics, because the point is that we need to sample an initial prior covariance. The point is that building a covariance is a huge step. So the matrix is huge. So we cannot formally build the prior covariance. So we need to sample members from a covariance that we are unable to build, but we need to represent it typically through low rank version or through the use of filters. So this is what we use here. So in fact, the way to build this ensemble is to generate some, to start from a mean model. We add some random perturbation in space, and then we filter the perturbation by local filter to satisfy some local correlation in space. And thanks to this, we are able to have a control of the prior covariance, which represents somehow some Gaussian-based shape in space. But this is not an easy to control the perturbation, because the amplitude of perturbation drives the kinematics. No. So this is not an easy task to design this initial ensemble, to check that we control the prior covariance, but also have some cycle skipping and so on. So this is a good question. They are, I think that what they are currently trying to do is to, they can relate that then to uncertainty basically on depth, because this is what they usually are interested to have uncertainty about the different horizons of interest for them and the depth of them and the thickness of them, because this is what is important. So basically, they use those kind of uncertainty to generate some kind of family of model in which they migrate higher frequency data to see the effect on the migrated sections. Um, yes, your point is good. Here we have done the uncertainty quantification with respect to the quality of the initial model. But one point of interest would be to do that with respect, for example, to tuning parameters. So to have the same initial models for all the members, a different tuning parameter for each member, and see how they translate in terms of uncertainty. So to not have uncertainty with respect to the velocity parameter, but uncertainty with respect to tuning parameter of inversion. And in such a case, we could have less parameter, and it would be less challenging in terms of quantification. This is something of interest. And for industry, this is clearly something that they would be interested in, because the practitioner usually have several or many buttons to touch, but at the end, it's few tens to hundreds maximum. It's not millions as we have here.
Okay, next, we have a question from our audience online. I will read it. It is from Mr. Ade Suryaputra, from Mr. Ade. So thanks, Dr. Brossier, for your presentation. I want to ask you, what is the impact of topographic free surface boundaries on inversion accuracy?
It's a good question. In fact, in the two examples I showed for the noise-based inversion, the topography effect are very important. On the landslide, of course, because basically only topography, so we need to well know the topography and well model surface wave and conversions associated to topography variation. On the Alpes scale application, I did not discuss, but we have a good representation of the sphericity of the target plus the topography of the Alps. And it is important because on the relay wave path, in fact, the Alps, we have some mountains. Basically, we have region on the water, so 0 meter altitude up to more than 4,000 meter high. So it really affects the kinematic of relay wave to account for this topography. For the marine case, it's all flat, so there is not really importance. In this case, yes, because actually it's the case, but we can simulate rigorous bathymetry if we need it. This is what we did also for the Alpine target. All the bathymetry, the Ligurian Sea, the well simulated. Simulate the inter depth to well simulate the short wave.
Yeah, okay, so yeah, thank you for your response for this online questions. I hope Mr. Ade can receive the response very well. Maybe one question from our students or our lecturers. Okay.
I do not a magic solution for this. We have this problem because I mean when we on our side, on our scale, when we compete with industry, there is clear difference in the computing success we have. I mean, we are able to run such kind of application up to roughly speaking 30 hertz with using the whole national machine that we have in France, while in the industry, they basically routinely apply that to 100 hertz. So, I would say two, not tips, but two targets to have in mind. Actively working on some GPU-based version of those codes, so to use GPU facilities that usually provide better peak performance, even if they are quite expensive, which does not completely solve the problem, actually. Also, one other direction is based on cloud computing. So even if you don't have facilities on site or everything gathered, using multiple remote servers with cloud computing is something possible. So, there have been several demonstrators by industry, in fact, that companies that do not have access to a very big machine, but they use Amazon-based or such kind of remote-based facilities. And what we are working on currently is to have a kind of workflow manager to be able to use heterogeneous platform, possibly multiple remote platforms, to run inversion without a big machine at once, as we did previously. But this is not really some solution to decrease the computational cost. This is more to use what exists in terms of computing facilities. So at the end of the day, the computing cost is the number of shots, time, frequency, power, and that's it.
Okay, yeah, thank you very much for your question. I think last one, I would like to have your final message for all of us here, probably in the wider context of this faculty. We have not only geophysics, we have physics, we have computer science, we have mathematics, and we have chemistry. So do you think each of these fields has contributions to what are you doing here?
For chemistry, it will be more difficult to have a clear answer, even if on the interpretation, petrophysics, and possible reservoir interpretation, I guess there are some works. But for all what I presented, clearly those kind of approach take benefit of multidisciplinary. Clearly, I mean, in our group, so we are basically computational geophysicists, but we have some students coming from geophysics. We have some lecturer and student coming from math, applied math. We have some student coming from physics. And it's really the combination of all those skills make such kind of project success. It cannot work with only geophysics, because we would lack mathematical concept, computational implementation. And I think as just the maybe final remark, I mean, the work I presented here as in the frame of the Seiscope Consortium, so which is a research group in Grenoble that we are leading. And I think one of the reasons why Seiscope is relatively active and well-known in at least in the industry frame is that we are able to tackle both some applied concept up to 3D realistic application. Some groups focus on concepts, but are not able to go toward application. Some group run application, but are lacking proposition in terms of new concepts. What we are trying to do is to have the whole scope of topics in the research, and think everything feeds each other, which is a good point. So as a final remark, I think that it's at least such kind of topic take benefit of all those fields.
I think our seminar today is concluded. And by the way, we will stay at our geophysics laboratory, so you can just feel free to come visit and maybe talk with him. It could be about anything, research, or maybe you want to live in France. Maybe you want to join his university, or you can ask such thing to him. And usually we have some small token of appreciation for our speaker, but I think we will provide it online. And also for our audience today, we will send the certificate of attendance for you online through your email. So thank you everyone for joining today. We conclude our seminar today. A nice holiday and long weekend. Oke, selamat siang semuanya. Terima kasih. Thank you.